So our next little unit, we're going to introduce potential and kinetic energy. And it's going to go hand in hand with work and power and what we've already learned so far, but we're just going to build that off it a little bit. And you'll see a lot of connections throughout this unit. Now, all forms of energy have the units of joules. And like we kind of said when we had work equals force times distance, it's also equal to the change in energy. So work is the amount of energy that something can do, therefore they're all going to have units of joules. Now, I just listed some different forms of energy that kind of came to mind. You might be able to brainstorm some others. So we got mechanical, which is going to be potential and kinetic. We got nuclear, electromagnetic, which is associated with electric or magnetic fields. Visible light is an example of electromagnetic energy. You got microwaves, radio waves, nuclear energy. I'm sure you saw that in chemistry. Thermal energy or heat energy, which is going to make really connect with our friction unit. And so when a force is exerted, a lot of times when the force of friction does work, it creates thermal energy. The way that we're going to define potential energy is just energy that's due to position or condition. So when we're focusing on gravitational potential energy, basically what that is, it's going to be the work done in lifting an object near Earth's surface. So by doing work, you're changing the amount of energy that the system has. So if you lift an object up, you do work on it, it's gaining gravitational potential energy. Now, I kind of left some space here because let's say we have the ground here, okay? Now, if I have some object, well, it doesn't really matter the mass of it. This object has 0 energy relative to the ground. But if I put a table here and I lift that object up and I place it on top of the table, well, now that object has gravitational potential energy relative to the ground. But if we talk about relative to the table, well, it's not above the table, it's on the same level as the table. So the amount of energy that it has relative to the table is 0 joules. So your formula for gravitational potential energy is PE, and you'll see it as the change in PE equals, let me try to fit it down here, mg times the change in height. So for this sample problem, how much energy is gained by an object with a mass of 2 kilograms that is lifted up from the floor to the top of a 0.92 meter high table? We got potential energy. Make sure you write your formula first. We got a 2 kilogram object. We know acceleration due to gravity is 9.81 meters per second squared. And we're lifting it up to a height of 0.92 meters. And multiply that out. And this object gains 18 joules of potential energy by lifting it up to that new height. Okay, so we're going to skip ahead. We're going to come back to Hooke's law and elastic potential energy. But kinetic and potential energy make it really easy to observe conservation of energy. So that's why we're jumping ahead. If you had physical science when you were in middle school, you definitely saw kinetic energy. I'm sure it's you've seen it in elementary school. It shouldn't be a new term. When we think back to kinetic friction, that's the friction due to the sliding of an object across a rough surface where static is not moving. So kinetic energy, we're going to keep the definition really simple, and we'll just say energy an object possesses due to motion. So anything in motion has kinetic energy. So if an object's moving, it has some amount of kinetic energy. And kinetic energy is given to us by the formula 1/2 mass times velocity squared. So when we start looking at some motion graphs, just be cognizant of the fact that that velocity term is squared. So we might, expect, depending on what is on the axis, we might expect a curve or an exponential relationship. So we could derive it if you use the formula work equals force times distance, and then you plug in F equals ma. You can derive this formula, and I could show that to you if you wish. But for now, just knowing Ke equals 1/2 mv squared, which is exactly how it's listed on your reference table. So we're given the mass, we're given the speed, and that's really all we need to figure out the kinetic energy of an object. So we can plug in, get 1/2, plug in the mass, make sure I plug in with units. Make sure I square that, don't forget to square it. And when you multiply that out, should get 3 joules of kinetic energy.